and I'm really happy to present Itzik Ben Shabbat. Itzik gained his PhD from Technion in 2019, and Itzik is a research fellow in Australian National University and in Technion. And Itzik will talk about octree-guided unoriented surface reconstruction. Please, thank you.
Thank you very much for the introduction. Actually, this paper was done when I was still a research fellow at the Technion at ANU. Now I'm just visiting research fellow at ANU. This work was led by Chamin, which is now completing his PhD, and supervised by Professor Stephen Gould. And yeah, let's dive in. So let's first talk about what the problem is. So the problem that we're tackling is surface reconstruction from unoriented point cloud. So given this nice point cloud, we don't have the normals to start with, so we just have the points. And what we actually want to get is the surface, right? So the surface, one way of representing it is the implicit representation, right? This means that the surface is basically the zero level set of some unknown function. Now, in the literature, there are two main ways to represent this. One is the indicator function, which you can see here on the left. So that means there's a clear inside and outside, 1 or 0, or 1 minus 1. And also the sign distance function, which is what we're currently using, is more common recently, which basically give you at each point in the domain, what is the distance to the surface. Here I will use this color gradient throughout the presentation. So outside is orange and inside is kind of greenish color, and the very light yellowish is close to the surface. Now there have been many previous works that dealt with these problems, starting from back in 2019, DeepSDF, occupancy network. They basically kind of tackled the problem, can we learn this using a neural network? And this was followed by a lot of papers, some of which by Lipman's group and some in our group, that basically tackled the question that, is there a better way to learn this? So proposing kind of initialization and regularization methods. And also the work by Sitzman et al. They basically asked, well, can we use a different activation function than ReLU? And they use the sinusoidal one. Now, before I dive into our approach, I kind of want to get this kind of common ground, establish it, so we all talk in the same language. So most previous works use the following pipeline architecture, right? You get a point as input, you feed it into a neural network, usually modeled using a multi-layer perceptron or MLP, and you get the distance to the surface, right? Now, the MLP is basically applying or multiplying a set of weights and adding a bias, and then applying activation function. Okay, so the way this looks in a 2D example, right? We have the point cloud on the left. We have these points lying on the surface. You feed them into the MLP, and then the output that you would get is something like this on the right. Right, you see the distances, and here I also highlighted the gradients or the normal vectors that you get, which are basically the gradients of the learned function. Okay, but there is a problem here, right? We saw that if you take away the supervision of normal vectors, you're basically getting a lot of what we call ghost geometries. So these ghost geometries are an inherent problem that basically the optimizer converges to a non-optimal solution, or rather an optimal solution, but that looks like this, right? You have a lot of these kind of bumps and clunks that are undesirable. And after working for a while in this space, we basically ask ourselves the question where, well, can we prevent these ghost geometries from happening? And spoiler alert, the answer is yes. And the way we did it here is by figuring out what are the inside and outside regions before optimizing the INR. So the key idea of this method is the two following steps, right? We construct an octree. This is why it's called octree guided. So we first construct an octree from the input point clouds, and then we do a labeling process where we label for each node in the tree which is inside and which is outside. And then only once we have that, we can optimize an implicit neural representation that can then that is then guided by the octree, right? And this gives us both better and faster surface reconstruction. When I say better, I mean more accurate. Okay? So now let's have a little bit closer look, right? So we have a 3D point cloud as input, no normals, and we first construct the octree, which you can see the different depths of the octree that you can get. Here, of course, we initialize by applying some constraint that the outer edges of the boundary are outside, and then we use a move-making algorithm, which is in the paper, and I do not have time to go into in full depth here, but we apply this, this move-making algorithm that optimizes for an energy function that basically states that we have every surface node touch an outside and inside, and also a minimal surface constraint. So the surface of the shape should be as small as possible. And then once we have this octree, we can use that to train the implicit neural representation that would give us the shape that we have here on the right. Now, how do we train this? We use the two traditional losses for implicit neural representation. So the zero level set loss, which basically pushes all points to be of zero distance from the surface, and all points on the surface to have zero distance, and also the iconal term that basically pushes all of the gradients of the network to be 1. But then we add these two L3 and L4 terms that basically take the information that we now have in the octree and impose it on the trained neural representation, right? So we have both the distance and the sign losses. Let's quickly look at a few qualitative results, right? So we compare to other methods like Siren, SAL, and our previous version of DIGS. DIGS, for example, creates this over-smoothed kind of shape, and especially these kind of places with holes. It really kind of bridges those gaps in places that it shouldn't. But our method, if you look at depth 6 or depth 7 trees, you can really get those high details that you want to get. If you want to look at it in a more visual kind of aspect, we're highlighting the different errors. So red here represents high error rate. You can see those Gauss geometries that I was talking about very, very clearly. And our method really shines there. I haven't mentioned this up to this point, but our method can basically be plugged into any implicit neural representation pipeline. It can be Siren, it can be NGLOD, it can be any INR training that you want. Feed it into our approach, you get the octree, use it for training, you get better and faster training and better and faster reconstruction. Which brings me to this kind of final slide of results, which basically shows that we can get up to 4 times speed up if you look at Siren, for example, which is pretty significant, while also getting a better accuracy performance. If you want to see more results, there are a bunch of experiments in the paper. Definitely check it out. So just to sum up, we propose OGINR, we construct an octree, label it inside outside, and optimize an INR. We also propose the energy function and the move-making algorithm, and this avoids local miniva for SGD. Before I wrap up, I just want to invite you to check out the Talking Papers podcast, which I host, and we have a lot of papers in this domain. So both DIGS is there, and Derek Liu's Lipschitz MLP is there. So definitely go check it out, completely free on your favorite podcasting app. And that's it. I would like to acknowledge the financial contribution of the Marie Curie Fellowship that funded this research, and also the NVIDIA hardware grant that provided the GPU to run the experiments. And yeah, all of the code is available on GitHub. There's a great project page that Chamin did, and I'm happy to take questions.